beginning. So thank you, Michael, for the shout out on some of the work we've done together with funding from the NSF. I'm a professor here at RPI, of course, but I also direct a center called LISA, Lighting Enabled Systems and Applications. Now that we've got LED lighting, what more can we make it do? So we basically focus on digitized color tunable lighting for people and plants and displays, advanced light sensors. You'd be surprised what the data in light can tell you about an environment. And then control systems and machine learning to be able to create sentient, immersive environments. This is a very wide range of things. So let me go a little bit to the next slide and show the areas that we work in. We work in the development of sensors and technologies for energy efficient buildings by harvesting the information in light and how light bounces around the space. I can develop much more efficient control algorithms, for example, for HVAC control to reduce building energy consumption. Similarly, I can figure out where people are in the building without using cameras, estimate what they are doing. In certain facilities, I can figure out where they're going and how they're interacting with each other. In hospitals, I can take a look for falls. I can determine normal motion patterns from abnormal motion patterns just by using the harvested data in reflected light, not camera systems, but various kinds of sensors we're developing. You've probably not heard of visible light communications. Perhaps you have, but you've no doubt heard of 5G. And you know that 6G and 7G and so on are coming. But the reality of the situation is that inside of buildings in particular, 5G and 6G doesn't work very well. And as you go to higher and higher RF frequencies to communicate, it becomes line of sight, just like light. And so many people, especially in Europe and China, are arguing that the future of 6G telecommunications is going to be a marriage of RF and light-based communications. We work in healthcare, not only sensing how people move, but of course the spectrum in light can impact human circadian performance, your sleep-wake cycles, and we fund work with other professors at RPI on work on how the spectrum of light can impact human perception as well as human health. And recently we got into plant science. Of course, plants use light. For plants, light is food, and the spectrum can really impact how they work. So where do we do some of this work? We're in the building CII on the 7th floor. We have the whole floor. We have an advanced design and control test bed where we can conduct a tremendous number of experiments. The ceiling is fully sensorized to detect where people are and how light is bouncing around the space. We can do Li-Fi experiments in here. The lighting is fully color tunable so that we can control the quality of the light, look at perception impacts, the way in which the lighting spectrum impacts how people perform, their productivity, their alertness. So we can do all of that. And this test bed is a very active space ordinarily, and we don't have a pandemic. And so we work on intelligent office spaces, intelligent buildings, focused on energy, and something called WELL. How can we design a building that helps people perform better and live healthier lives? And this has become a very, very big research area at universities throughout the world. I mentioned plants. I'm going to show a spectrum over here. Believe it or not, this is red lettuce, but it doesn't look very red because we grew it under a spectrum to make it grow fast. Now, if I change the spectrum on purpose, in 24 hours, I can change my green red lettuce into red lettuce. And I'll just kind of play this movie very quickly over here. And you'll see that the plant, contrary to being passive, is actually kind of mobile. But you see, just by changing the color of lights used to illuminate the plant, or irradiate the plant in our case, you can change green red lettuce to red lettuce. Not only that, we found that by pulsing the light and timing it to the photosynthesis cycles of the plant, we can actually make it grow faster, up to 30% faster. For the same amount of energy. So not only that, we design biosensors for the plants. So we can take a look at the plants and measure the spectroscopy of them, figure out how to use light and other environmental factors to make plant growth more efficient. Now, those aren't the only areas that we work on. Similar to Professor Shore, who you just heard talk, we were fascinated with LED research. That's actually my background of research. And this is one of the publications that was joint with Professor Paul Chow on the monolithic integration of gallium nitride transistors and gallium nitride LEDs all in the same chip. And this may not look like very much, but the fact that I can put a transistor out of gallium nitride, not silicon, but gallium nitride, with an LED made out of gallium nitride, means that now I can build all kinds of advanced LED sensing technologies and transmission technologies. I can turn that LED on, off very fast to transmit data. I can actually operate the LED as a detector and use a transistor array to build a video transceiver. We have filed a patent on this concept of using an actual LED display in a phone as a display, but also as a transceiver for being able to send and receive data in that brave new 5G, 6G world where light is going to participate with RF in communications. So this is kind of a range of the technologies we work in. And lately we started to move into this concept of smart systems, smart buildings, smart lighting, completely sensorized. How can we bring autonomous systems for control of buildings to life for people? So we take data, look at putting that into information, into applications. And we're looking at smart building and smart city applications. Ultimately, we're focused, and our tagline is kind of systems that think. How can we convert raw data, which is basically IoT, into knowledge and wisdom? And of course, this is a hot topic for many faculty throughout RPI and including in ECSE. So we're working at the sensor end, new sensors and applications of those sensors for human wellness, for data information, communications, and even for the food we eat. So with that, I'm going to end.